Swayam Prabha. Digital India. Educated India.
Welcome to lecture 3 of week 6 of our NPTEL course on Muffler acoustics. For this class, we are going to discuss about wave propagation, one dimensional wave propagation in conical ducts. So, we have our 1D waves in conical ducts. So, you see here this is a schematic of a conical duct and the wave propagation, let us say this is the inlet and this is the outlet. So, what we are going to do is basically use our Webster's Horn equation to study acoustic wave propagation in such a system. So, as you see it is given by the following, x being the, let us denote this direction by x. So, as we know it is given by and we have your Webster's Horn equation or one dimensional equation. Now, for a conical duct we can, let us look at this schematic a bit carefully. Now, Sx could be varying in any form using any functional form, but for a conical duct how does it vary? So, if we consider the radius to be given from this section r is a function of Rx. So, the question here is that how is radius varying? So, for a conical duct the radius is linearly increasing. So, R then is basically something like R is equal to R naught plus alpha x, where R naught is some constant. So, basically we can consider R naught to be something like this and plus alpha could be the slope. It is basically related to tan theta. So, if you consider this theta angle, like I said, theta is constant for a conical duct, that is the rate or the flare angle is constant throughout the cross section, that is the slope is constant. So, basically alpha is tan theta, theta is the flare angle. Okay. Now, the thing is that how do we go about solving for this thing? So, a better way, perhaps a little more simplified way of doing this stuff is to assume some kind of a hypothetical or some kind of a point here where R naught is 0. So, let us actually do the following, instead of measuring x right from here, let us say we measure x from here where x is 0 here and it has certain value, say x1 here and x2 here, okay, x1 here and x2 at the other side. So, in that case I would write R or the radius to be directly proportional to x, that is radius is increasing with the axial distance x. So, since area is pi r square, that would mean that S is proportional to x square also. X is a cross sectional area is proportional to the distance from the hypothetical apex, let us say O. So, what will this imply? This implies that ds dx is proportional to 2 times x, and this would further mean that 1 by s into ds dx is equal to 2 times x. Okay. So, we probably can substitute this guy in this equation, the Webster's equation. So, what do we get? We get dp by dx plus k naught square operating upon p is equal to 0. So, how do we go about solving it? It might look a little difficult to solve, but remember we have the transformation. So, if we put p is equal to or P tilde is equal to say q, where q is another variable, q by x. Let us see what we get. Let me box this equation. So, what this would mean, q by minus x square plus 1 by x into dq by dx. Okay. So, we get the following. With this particular thing, we obviously can put all this stuff here, and other than that we probably have to differentiate this guy again to get the following. Let us do a term by term differentiation. So, basically once we do that, it is 2 by x cube times q, then we will get this thing, plus we have contributions due to the other terms. So, because of the lack of space I am just directly writing it, 1 by x dq dx2 and your minus 1 by x square times dq dx. So, what we get here is that we probably can put this as, get rid of this guy and put it 2 minus 2 by x square. We get this. Now, what we will do is that we will put this term here and this term here. So, and then we will simplify, 2 by x cube into q minus 2 by x square into dq dx plus 1 by x times d 2q by dx square. We write this and then we will multiply this by 2 divided by x. So, what we will get? We will get plus 2 by x times minus q by x square plus 1 by x times this thing plus k naught square p, or p is again actually q by x. With this substitutions, what can we expect? We can expect that, well, this term and this term cancels away, right, and here you have minus sign sitting here, is not it, and you multiply this thing. So, this sign and this will sort of go away, and 1 by x we can take common, to get the following. So, basically this term, the circle term, that must be equal to 0, because we are talking about general x. So, I would write this thing in a nice clean slide, t 2q by dx square plus k naught square q is equal to 0, is not it, where q understandably is the function of x. So, now the solution of this should be fairly straightforward. Q as a function of x is given by c1 times exponential e to the power minus j k naught x plus c2 times e to the power j k naught x. Now, remember q was given by p tilde into x, or p tilde is equal to q by x. So, basically what it would mean is that p tilde is equal to 1 by x times c1 So, we get the solution for the one dimensional wave propagation in a conical duct, obviously with a constant flare, and that flare angle we can decide basically once you obtain the thing like transfer matrix. So, in that thing we can specify the radius at two sections. So, for example, if we have a conical duct like this, so this is in terms of general x, where x is measured in here. So, once we specify r1 and r2 and all obviously x or L the distance, then the slope is given by tan theta, which is nothing but r2 minus r1 by L. We have our 3 parameters to decide the slope, the radius at the 2 sections and how far apart these sections are, which is sort of a kind of a common knowledge. So, this is the expression for the acoustic pressure field. Can you see any resemblance with the spherical wave? In fact, this particular equation that we got, this thing, this equation itself is basically the same as the equation for the spherical waves, one dimensional spherical wave equation. Let me write down the generalized form of the spherical wave. So, here note that we are making a small but important digression. It is important to understand certain things conceptually. Spherical wave equation, or basically wave equation in spherical coordinates. So, basically that is then 1 by r square and r square times phi r into r plus 1 by r square sin theta and sin theta times phi theta and theta and minus phi times dt by c naught square is equal to 0, of course, where phi can be any function. Here let's actually replace phi by p tilde, where p tilde is now the acoustic pressure. So, here theta suffix means derivative with respect to theta, and actually what we have done here, we have purposely we have kind of omitted your the phi term. So, spherical coordinates comprises of r, radius, and theta, that is your polar angle theta, and phi, which is your azimuthal angle. So, we have not really considered the phi coordinate. Let us be happy with only r and theta coordinate. So, let us be happy with that and go about solving this equation. So, once we put p tilde is equal to some function of r, capital R, times theta, capital theta, which is function of theta. This can be obviously, we can straight away simplify things by insisting time harmonicity. So, we get this. So, once we substitute this particular part in the above equation, what do we hope to get? We will get r square times r derivative with respect to this r square times r plus sin theta times the function this thing theta and whole theta and r square sin theta and the function theta is equal to a naught square. After simplifying things, we will get general thing that the solution for this particular part, this will separate out and we will get the Legendre function. So, the solution for that is like 1 minus z square and the differential equation, I am sorry, and your this thing and dz square minus 2z times d this thing and dz plus some constant c, which turns out to be n into n plus 1. So, readers are urged to, or students are basically, viewers are urged to have a look at the book by David Blackstock on fundamental of acoustics, or possibly Kensler and Frey for a detailed discussion and development of these equations. And here of course z is equal to cos theta. We basically separate out this form, evaluate it to be a certain constant and substitute z is equal to cos theta and carry out the algebra to arrive at this thing. The solutions of the above equation, this is for theta, and the reason that I am telling you, because this will have a dependence on n. So, where n is an integer ranging from 0, 1, 2 and so on. So, the solutions of this thing is given by the Legendre function of integer order, which is basically a polynomial in z and with the range being from -1 to this thing and this particular thing. So, we have this kind of a thing, or theta alternatively ranges from 0 to pi. Now, it so happens that once we decide on a particular n value, the spherical wave equation can then, or the radial part of the spherical wave equation turns out to be, after obviously some simplifications, the following. So, we get the following. When we substitute n is equal to 0 in the above equation, we will get the following. Note that this particular form, this particular equation is identical with this part, with this equation, where the only difference is that x is replaced with r, and here p was a function, p tilde was a function of the axial coordinate measured from the hypothetical apex x, and here it is measured also from the hypothetical apex O, and this is the radial coordinate. So, r then is measured from the hypothetical apex of the cone O, and r can be anything here. If it is at this point, it is r1, at this point it is r2. So, basically what it would mean, it would mean spherical waves that go like this, but axial waves, how do they go? They go like this, but the form remains the same, and here we need to specify the radius from this thing, and here we basically need to specify the axial distance. So, there is a difference, x is measured along the axis, here r is the radius, it can have any angle, but we specify it to be r1, r2. So, basically the Webster's Horn equation for one dimensional waves in conical ducts is identical with the spherical wave equation for the 0th order mode. That is, basically there is no dependence on the polar angle, and of course no dependence on the azimuthal angle as well. So, where do we go from here? It is now, I guess, time to derive the expression for the velocity. So, we again resort back to the linearized Euler equation. Remember, momentum equation for the conical duct does not change, or basically for any duct with a gradually varying cross section area where the flare is not varying very rapidly. So, your momentum equation is pretty much the same as rho naught times del t of u is equal to minus this thing. Now that we know it is of this form, j omega and this is u tilde times and minus x. So, after some algebra, basically once we need to take a partial derivative of this part, C1 times this particular thing. So, after some algebra, we will figure out that u tilde x is given by j omega rho naught x, and in the bracket. So, this is what I have already worked out, is given by minus j k naught times minus 1 by z, and C1 is a constant now, arbitrary constant of integration, it is x k naught x and plus j k naught times 1 minus z times C2 into e to the power j k naught x. So, we will get this guy. So, we have the expression for the particle velocity. Now, clearly if we multiply both the sides by rho naught and get rid of the term here and multiply here by C naught and then C naught. So, here you will get, we will get K naught, and actually there will be an x sitting here, not this thing, there will be an x here. So, we will get this thing. So, this will give you the, and actually when you multiply this by the cross sectional area at any point, this multiplied by say S x, let me just get rid of this thing u into S x So, we will have your Sx sitting here, and Sx is a function of x. So, now what do we need to do for a conical duct is that we need to fix our axial coordinates, that is where are we heading at. So, here at x1 and x2 like I have been talking about. So, once we get those values or once we decide what is our x1 or x2 value or the length L and obviously the radius at both the points. So, then we can formulate the transfer matrix. To do so, we will probably take up the transfer matrix derivation in the next class, lecture 4, and after that for a generalized element. And what we will do is that our objective will be to get the transfer matrix for a conical duct from this point to this point exactly like we got for a uniform duct. So, we will get the transfer matrix in this form where we will get the 4 pole parameters between point 2 and 1 like this, and then it will be good learning exercise if we could do the following things in the next class. Firstly, show that the transmission loss for a conical duct basically a diffuser kind of an element even when there is no sudden expansion. Remember, these are progressive discontinuities. So, the waves are going like this. So, the idea is that because the area change is gradual, there is a finite some finite area change is there. So, transmission loss will never be 0 even if we do not have any sudden area discontinuities like just like we have a system here. But if you have a system like this thing, instead of a diffuser kind of an element, if we have a muffler with a sudden expansion, but only difference is that now we do not have a uniform section, we have a section with gradually varying flare, a conical muffler, a muffler which is conical. In such a case, we will also derive the one dimensional transmission loss based upon one dimensional theory without mean flow effects, of course. So, that will be our goal for the next class, next lecture, and in the final lecture of this week, we will probably talk about some advanced techniques like segmentation approach and all that and how they can be used to handle complicated ducts, more general theories. So, thanks a lot, thanks for attending, stay tuned.